This is the last section of the chapter, and it's called bond enthalpy, and bond enthalpies are symbolized by the letter D. Originally, if you have an earlier edition, it appeared in chapter 8, so I've had to kind of rearrange things. The take-home message from this entire chapter are these first two bullets. Energy is consumed when bonds are broken. And if you see this, let's pretend we're breaking this bond. It's going to take energy. It is going to be an endothermic process. I can now say that since we've had the chapter. Energy is going to be released when bonds are formed. Think about it. If you have a diatomic molecule and you make two individual atoms, you have to put in energy. If you reverse this reaction, and you've learned what happens when you reverse things, if two A's come together to give you an A2, the energy has to go on the other side. That's a concept that we really want you to grasp from this chapter. Now, in this section, we talk about bond enthalpy symbolized by the letter D. And it is defined as the energy that's required to break a covalent bond. I realize covalent bonds come in chapter 8. This is where this section used to be, but someone decided to put it into chapter 5. So let's talk about hydrogen. If I break a hydrogen bond, it costs 436 kilojoules. If I break a chlorine bond, it costs only 242 kilojoules. So what that tells me is the H2 bond is stronger than the Cl2 bond because 436 is a bigger number than 242. It also implies that hydrogen is a more stable molecule. It's less reactive than Cl2. So if you take anything away from this chapter that you're going to use someplace else, I would say it's found on this first slide. Let's keep going. If we look at something like water and we break all of the bonds and we get hydrogen, two of them, and oxygen, the delta H is 926. So you would expect that the bond enthalpy would only be 463, dividing it by 2. But it's a little more complicated. 501 kilojoules for the first bond, 425 for the second bond. We don't go into detail, we just want you to realize that. I have a lot of just things typed here because it's extremely factual. So let's move on. As you increase the number of bonds between two atoms, you're going to need more energy to break the bonds. Here I have a single, here I have a double, here I have a triple. So you can see that the kilojoules are definitely going to increase. It's not linear, it's measured. And also, as the number of bonds increases, they're going to be shorter. My bond length goes from 1.5 to 1.3 to 1.2. Again, you do not have to know the numbers, you just have to know the trend of what is occurring. So what's the rest of this section look like? Well, we can use bond enthalpy to estimate a delta H of reaction if we don't have the right data to work with. So values for bond enthalpies are tabulated. You can just see like a CH is a 413. You can pick over here an HH is a 436. I can find the chlorine from my earlier slide. They're all tabulated for. So you'll be faced with a question like this. What is the delta H of reaction using the bond energy D? I have ammonia reacting with chlorine to form nitrogen and HCl. What you need to do is draw out the structure. That's why this is kind of hard in chapter 5. It's a lot easier in chapter 8 when you've learned how to draw Lewis structures. I have two ammonias. I've just drawn them right here. I have three chlorines, 1, 2, 3. And those are my reactants. They're going to form nitrogen, which has a triple bond, and it's going to form 6 HCl's. And you know how I say somehow you have to trust me? Well, here's a part where you just have to trust me because that's just how life goes. So if you're given a problem like this, hopefully you will have gone through chapter 8 before they ask this. But what you do, and this is so different because you take the bonds that are broken. So that is the reactants, and you subtract from it the values for the bonds that are formed, which is the products. If I look at what I've drawn, I see that I have 6 nitrogen-hydrogen bonds. 1, 2, 3, 4, 5, 6. If I look at the chlorines, I have 3 chlorine-chlorine bonds. So if you notice, the first line of my calculation shows 6 Ds for NHs, 3 Ds for Cl. It shows a nitrogen triple bond, and it shows 6 HCl bonds. So I go into the table, I pull out the numbers for each of the different bond values, and I just do algebra. So again, I am very picky. I don't like people to jump to an answer unless they can defend it. And essentially, you see the answer here by crunching the numbers as coming up to be a number which is 455 kilojoules. And it has a negative sign. That means this is an exothermic reaction. Okay, so that's one example. Another example is, well, not another example. You could do the same process using the heats of formation. I'm not going to talk through it. You can go through it by yourself. All of these numbers come out of a table, and being Hess's law, what we have are products, and we subtract from them the reactants. Putting in the numbers, what we get is minus 461. And I like to say that these answers are in the same ballpark. They're probably not going to be the same number. When we had done heats of formation and delta H0 of reaction, we really did get the same number. Here, when we switch to bond enthalpy, they're not going to be exactly the same. But again, you're not expected to use it unless you are asked. Here is yet another example, and I'm going to draw it out. This molecule is ethylene, and you will learn about it as we get deeper into the course. You'll learn about sigma and pi bonds, but there is one ethylene, and if you've heard of polyethylene, milk jugs and plastic bags, that's the starting material. The other reactant is bromine, Br-Br bond, and what you make is this molecule. It's a bromoethane. All right, that's the organic name for it. We have bromines that have added across the double bond, and what you would do here is the exact same thing. I see 4 carbon-hydrogen bonds, I see 1 carbon-carbon double bond, and I see 1 bromine-bromine bond. So again, it's looking up the values, plugging them in, and coming up with the answer. That's again the reactants. They are in the beginning, and it is products. What do we get when we form the bonds? Well, we get 2 BR-C bonds, and we get 4 CH bonds. So what you can actually do in this problem is say, I don't have to even use the CH bonds, because they are on each side of the equation. I only need to look at the unique product bonds. Again, I will let you work through math. What I want to finish up this chapter with is the reason why we did it. Remember in the beginning of the chapter, I said you will be able to create an enthalpy diagram for propane combustion. Here we have our reactants, propane. Here we have our products, CO2 and water. By working through this chapter, you now know what is a delta H1, what is a delta H2, and what is a delta H3. That's what we're going to explain as we wrap up this chapter. You know what a heat of reaction is, and we're going to show that also as we work through it. So if someone were to ask you to create the diagram, here is propane, there is oxygen, you would write, and then you would have to balance the chemical equation. Just what you learned all the way back in chapter. If you look at our picture, here is our endo process, here is our exo, and here is our exo. Again, the other piece was the delta H0 of reaction. Now you can actually see 3. Then what you would do is what we've taught you in this chapter. You would write and balance heat of formation equations. Here we have our C3H8. It must have a 1, so we adjust our coefficients accordingly. Here we have a CO2, adjust those coefficients. Here we have 1H2O, adjust those coefficients. Those are all the components of the chemical equation. This is a reactant. These two are the products. And as we've just gone through in the sections, the first one you have to reverse, the second multiply by 3, the third you multiply by 4. So once you write that all down, you would add up the individual equations. Here we get a positive 1.103. That is the endo process. Here is an exo. Here is an exo. I don't like to go back in terms of a slide, but I kind of have to. I could figure out to do it. But that is where that diagram comes from. You now know how to write heat of formation reactions. You now know where to get the actual numbers from, and you should make sure that you can teach yourself where they go on the diagram. Where that comes from, it is from when we have rearranged and balanced the equations, we've added up the individuals, and that gives us the heat of reaction. So the take-home message is, you now can draw and label an enthalpy diagram. You would have an arrow going up for an endo reaction because it's a positive delta H0 reaction. You would have an arrow going down for an exothermic reaction because it is a negative. So I've also put a little picture here because not every reaction is going to be combustion of propane. So I'd say this slide represents insight. You've had to teach yourself facts. You've had to teach yourself methods. You've learned how to solve problems. Now you have some insight and you know how to draw one of these diagrams. Remember, breaking bonds is an endothermic process. You have to put energy in. When we make bonds, it's an exothermic process and energy comes out. When you look at the two, you see what is their balance, and that will tell you whether the overall reaction is endothermic or exothermic.